Hello, everybody. Thanks for watching today. So I'm going to continue to cover Chapter 2, Section 7. And if you recall in the last video, I showed you what an inverse function is and how to verify two functions are inverses of one another. What I'm going to do today is I'm going to go over what graphs of inverses look like and how we can use those graphs to possibly verify whether two functions are inverses of one another. So before I do that, though, I want to make sure I mention again that I don't want people to be confused by the use of -1 to denote the inverse function f inverse. In this section, whenever f inverse is written, it always refers to the inverse of the function f and not to the reciprocal. Please understand that the inverse and reciprocal are not the same thing. In this section, the -1 power is going to refer to the inverse. It says if the function g is the inverse function of the function f, it must also be true that the function f is the inverse function of the function g. And it says for this reason, you can say that the functions f and g are inverse functions of one another. And that's why they use that notation f of x and then f inverse of x, because it's denoting a relationship between the two functions, that those two functions will undo each other. And if you recall from the last video, the way that we show that they undo each other is that you compose them together. And when you compose them both ways, you will get the identity function both ways. All right, so let's take a look at what a graph of an inverse function looks like. So if you look at this function, the first one I'm going to trace here, you can see, and this is just an arbitrary graph. You don't even need to know what the actual equation is. But if you look at the graph of its inverse, what you're going to see is a very similar shaped graph. However, it's a reflection. And so what you see is these two functions are inverses of one another. And since they're inverses of one another, they will end up being reflections of each other about the line y equals x. And so this line, this diagonal line that you see going right down through the middle there, that's the line y equals x. And so if you have a graph of two different functions and you look, you should be able to recognize whether they're reflections of each other about that line y equals x. If they are reflections, then that means they're inverses of one another. One other piece of this graph that I want to make sure that I bring your attention to is this ordered pair. If you look at this function, there is an ordered pair a comma b. An inverse function will have the inverse ordered pair of a comma b, and that ordered pair is b comma a. So essentially what's happening is every single ordered pair on this line, the x and the y end up flipping. And so what was x here and y here now becomes the x and then the y. And that's what happens, and that's actually how you can graph very easily inverse functions, is if you have a function, you can put some ordered pairs on the drawing of the graph that you have, and then just flip-flop the x and y's and regraph them, and you'll have the graph of the inverse function. So this one is example 2a, and it says sketch the graphs of the inverse functions f of x equals 2x minus 3, and then f inverse of x equals 1/2 x plus 3. So I'm going to go ahead and draw a coordinate plane first. And then what I'm going to do is I'm going to graph this first equation, f of x. I'm going to graph it in red. So I'm going to go down 3, and I'm going to put a dot. And then I'm going to go up 2, over 1. And I will put another dot. And you can see this would be a line of this particular graph. That's close enough right there. Now the second graph, I'm going to go ahead, I'll graph that in purple. This is going to have to be cleaned up a little bit. I do need to distribute the 1/2. So I'd get f inverse of x equals 1/2 x plus 3 over 2. So what that means is the y-intercept is what at 1.5, and then I go up 1 over 2 right there, and I get another one, and then I would get my line right there. Now the last thing that I want you to see is that both of these lines are a reflection about that line that's running right up through the middle. Now, I'm hand drawing this, so it's not perfect, but you can see that if I would spin on that dashed line, those equation or those graphs would line right up with each other. So that does verify that those two are inverses of one another. Now, if we wanted to make absolutely sure, you could take those two functions and actually compose them together. But we're not going to do that right now. Now, here's a better graph of what I just showed you. And you can see in this graph, they went ahead and they actually put and labeled some of the ordered pairs on there. So you can see I have -3, 0, -1, 1, and then 1, 2. Well, if I look at that point 1, 2, if you look right over here, I've got the ordered pair 2, 1. The same with the -1, 1 turns into 1, -1, and then -3, 0 turns into 0, -3. So all the ordered pairs from the original function flip, and then we get the ordered pairs for the inverse. Now, another concept that we need to discuss before we start finding more complex inverse functions is what it means to be one-to-one. And what a one-to-one function is when each value of the dependent variable, which is the y variable, corresponds to exactly one variable or value of the independent variable, which is the x. A function f has an inverse function if and only if f is one-to-one. So what this is saying is that you can only have one y paired with one x. And if it's not the case that that's true, then you won't be able to find an inverse for the function. So this is where it gets really tricky. Not all functions have inverses, or you could say not all functions are invertible. And you have to test for this prior to trying to find the inverse so you don't waste your time. Now, if you recall, we had a test called the vertical line test. And what the vertical line test looked for is it looked for when we had multiple x's or repeated x's. So if I drew a little graph of something that would fail the vertical line test, something like this, a sideways parabola, if I went out here, this would have 2 points that would line up vertically, and therefore it would not be a function. So like this point would be 3, 1, and this point would be 3, 3. Because the x values are both 3, this would fail to be a function. Well, one-to-one, not only can you not have repeated x values to be a function for one-to-one, you cannot have any repeated y values. So as an example, I'm going to go ahead and stick with that parabola. If I wrote a parabola like this, and I went out here and wrote an ordered pair here and here, that first ordered pair we'll call 2, 1, and then we'll call this one -2, 1. For one-to-oneness, we cannot have any repeated y values because you can see that y is connected to a 2 and a -2. So this would not have an inverse because it fails. Now, what we're looking for is we're going to do something called the horizontal line test. If you pass a horizontal line through a graph and it intersects in more than one place, then it is not one-to-one. So it's a really simple test that we can use to figure out whether a graph is one-to-one and then know whether we should try to find an inverse. So it says, note in the following list that if point AB is on one of the graphs of F, then the point BA is on the graph of F inverse. And that's what I showed you with this, where the ordered pairs flip-flop. Okay. Now, this says determine whether the following functions are inverses of one another by graphing. All right, so what we're going to do is we're going to go ahead and graph these. Now, we don't need the use of a graphing calculator for this, although I'm going to show you some graphs from it, but you should know your parent functions well enough now to be able to sketch the graph of both of these. And that's kind of the idea of learning those parent functions. So I'm going to go ahead and draw a coordinate plane. You can see the first one is f of x equals x squared. Now, it does say when x is just greater than or equal to 0. Now, why does it say that? Well, if I were to graph the regular parabola, I would have something that looked like that. and this. And this comes back to what I just got done showing you about functions needing to be one-to-one in order to have an inverse. This would not have an inverse because if you passed a horizontal line through it, it would intersect in more than one place. So what they have to do to create or make this function have an inverse is they have to put in a restriction on the domain of the function. And the restriction here is that x can be greater than or equal to 0. So this comes back to like when we learned about piecewise defined functions. Basically, what they're saying is they don't want that side of the graph. They only want the side of the graph that is greater than or equal to 0. Now, by eliminating that left-hand side, we now have a function that passes the horizontal line test and therefore can be inverted. Now, the square root of x, that's another one. That's one of our parent functions, if you recall, starts at the origin, goes up, and then comes over like this. And what you hopefully see is that these are indeed reflections about the line y equals x. If I draw a diagonal line right up through there, you can see that they are reflections of one another. And if you look at the graph, there's an actual graph from a graphing calculator. You can see that they are reflections. All right, guys, that's what I have for you today. Hope that made sense. And as always, if you have any questions, feel free to email me. Have a great day.